Abhisek Arya. I am the head of Department of Civil Engineering, JIT Jodhpur. The topic today which we are covering is shear force diagram and bending moment diagram. It is very important for a civil engineer to actually understand what is shear force and what is bending moment, and to draw the diagram for any type of beams for any types of loading. So today we will cover this particular topic. Now, first of all, there are two terms. First term is shear force, and the second term is bending moment. Before entering into this topic, we will first of all talk about what is a beam. A beam is a horizontal member which is subjected to transverse loading. Transverse loading means if we see that this particular thing is a beam, then transverse loading means the loading which is applied like this on the axis of this, whereas longitudinal loading means if we apply the load like this, it will be called as longitudinal loading. But in the civil structures, like the beams which we see in our houses or our structures, it is always a transverse loading which is applied on it as point load or UDL, which I will tell you later. So this is called as beam. We can draw the beam like this, which is having a cross section, this. But in the analysis or whenever we solve the numericals, then we draw the beam like this with the end conditions. Now, what are the end conditions? There are three end conditions, or you can say there are three types of supports which a beam is always subjected to. The first one is known as roller support. The second one is known as hinge support. Whereas the third one is known as fixed support. The symbols of these supports are now, if we can see that these three supports or support conditions are there, but the point is we first of all need to determine what exactly are the unknowns or the reaction components which come in every type of supports. First of all, if we can see this particular symbol of roller support, we can see that this particular support can always take a vertical loadings. That means it will give a reaction which is the vertical reaction. If we give name to this thing or this point, then the roller support will always give a vertical reaction. So it means that it is the one unknown which we have to determine in roller supports. Now we talk about the hinge support. Hinge support gives both vertical and horizontal reactions because the translation moment is always restricted in case of hinge support. But if we talk about the fixed support gives three things. The first one, as we know this thing, is vertical reaction. The second one is the horizontal reaction, and also fixed support actually also judges the moment, or it does not allow the movement of any beam. If you want to understand this particular two things, then hinge support is always like this thing. This is a hinge support. If this particular beam is moving like this, then we say it as a hinge support. Whereas if it is a fixed support, then there will be no displacement or movement which is allowed. Now for a civil engineer, what exactly are the implications or where we see these supports? In reality, in our structure or in our construction, we don't have hinge supports, but mostly we have fixed supports. But still, for the analysis purpose, whichever we do in our structure, we if the work is done by stone, that means if the walls are created by stones, and then if there is a RCC slab or RCC beam is there, then those particular support or those particular beams are analyzed as hinge support. Whereas if the RCC work is there, that means the foundation and the columns all are created by the RCC work, and if then we have a beam of RCC, then that particular beam is known as fixed beam, or the supports are known as fixed supports. Now we can quite easily see that the roller support gives one unknown, that is vertical reaction. The hinge support gives two unknown, and the fixed support gives three unknown. So we have to determine these unknowns by the methods. Now we will define these particular two terms, shear force and bending moment. So first I am making one beam. These are two supports. If we have one fixed support, one hinge support and one roller support, such type of beams are known as simply supported beams. Such type of beams give you two unknowns from this support, that is a hinge support, and one unknown from the roller support. Now to determine these three unknowns, we have three equations. The equations from the equilibriums are this, that means all the horizontal forces. If the beam is in equilibrium, then all the horizontal forces will be also in equilibrium. That means the summation of all the horizontal force or the algebraic sum of all the horizontal force will be 0. In the same way, all the vertical forces will also be equal to 0, and the moment applied at any point will also be 0. That means at any particular point, if on the left hand side there is a downward movement or hogging moment, which I will define later on, or in the right side if the sagging moment is there, then these particular two moments will be as the value wise they will be equal, whereas in the direction they will be opposite. So the resultant moment on any particular point will also be 0. Now this particular simply supported beam, if we apply point loads. Now what exactly is point load? Point load means a load which is actually applied on a single point. In real life, because we are talking about the civil engineering perspective, in real life in our civil engineering there are no as such point loads which are available, because every load is scattered on some sort of area, and if the load is scattered on some sort of area, then it is not known as point load, it is known as UDL. The full form of UDL is uniformly distributed load. For an example, all the types of load which we see in our house, like flooring, like roof, every load is scattered on some sort of area, and the intensity of load, for an example, the floor on which right now I am standing, in this particular floor also, if I am standing there on the corner side of this particular room, then also the thickness of the floor or the construction of the floor is same, which is in the right side or the middle portion or every portion of this particular room. So that means that this particular load is known as uniformly distributed load or UDL. Point loads are never advisable in any type of structure, because it is very difficult to design such type of structure, because point load actually applies on one single point, and that it can create very harmful problems for a civil engineer to create a structure. But in the analysis, yes, we have point loads, or sometimes the loads like the loads of almiras, the loads of small things like fridges, coolers and everything, they can be considered as point load. Now we come back to this particular beam. This particular beam, which is known as the beam AB, and as I defined, this particular type of beam is known as simply supported beam, because one support is fixed and one support is hinge. Now this particular beam is subjected to 2 point loads, W1 and W2. Now we actually analyze this beam. Now this particular beam is subjected to 2 point load. Now if we analyze this particular beam, if it is in equilibrium, then there will be, as we know, there will be 2 vertical components of reaction, that is VB and VA. Because this particular support is a hinge support, then there will also be a horizontal reaction. But if the beam is not subjected to any type of horizontal loading, or it is not subjected to any type of inclined loading, then there will be no horizontal force. And if there is no horizontal force, then there cannot be a horizontal reaction. So the horizontal reaction component at the point A will be 0. That means HA will be 0. So there is no need to write this thing. Now we start analyzing this particular beam. Now if I take a single point, any arbitrary point x, which is situated at x meter from A. It is also arbitrary. We can take the distance from any side, which I will tell you at the later stages when we will solve a numerical. Now we want to analyze this particular point x. That means I have cut this beam at this particular place, and this is known as a cross section or a section which we have cut. Now if I draw this beam again, then this will be point x. In the same way, this will be now. If we say that this particular whole beam is in equilibrium, then these both portions must be in equilibrium. Now if you see this particular part which we have cut from the beam, then this particular part is having two components, two forces. One force is VA and the other one is W1. If we assume that VA is greater than W1, then quite easily we can see from this particular part that the resultant or the net force in this particular part will be because of VA, that is VA is dominating on W1, and the net tendency of this part will be to go on the upward side. So, but the case is not there, it is not going upwards. Then it means that at this particular point there has to be a force which is on the opposite side of the net tendency, that is the downward side, and the value of this must be in order to make this particular part as in equilibrium. So now if we draw this particular part, or if we analyze this particular part, we can quite easily see that the net resultant force is 0 because VA is going upward, whereas W1 and VA minus W1, these both are going downwards. So this particular part is in equilibrium. Now if we analyze this particular part is having two components once again. The first component is W1 and the second one is vertical reaction at B. Now as if we talk about this whole beam, and as we talked about the sigma V is equal to 0, that means all the vertical forces are 0, we could have deduced one equation, and the equation says that VA plus VB must be 0, or must be equal to W1 plus W2. It has to be there in order to make this particular beam in equilibrium. So from this equation we can deduce that if VA is greater than W1, then W1 has to be greater than VB. So now if we talk about this part, now we have the conclusion that W2 is greater than VB. Then if we see, W2 is having the tendency to move this particular beam downward, whereas VB wants this particular beam to go upward. So what will be the net force? Net force will be W2 minus VB, and the tendency of this particular part will to go downward, whereas once again it is not the case. The whole beam is in equilibrium, that means every part of this beam is also in equilibrium. So now it means that this particular part is in equilibrium and this particular part is also in equilibrium. So there has to be one force which is applied at this particular point, and in such a manner that the whole tendency of going the beam downward has to be resisted. That means the direction of this force will be upward, and the magnitude of this force has to be W2 minus VB. Because now if I see this particular part, then we can quite easily say that this whole system is in equilibrium, because the force W2 is going downwards, whereas VB is going upward, and also W2 minus VB is also going upward. That means the net force is 0 in this part. So now the point is that if we talk about these points, in reality it is not the case. The case is it is the beam. the beam is in such a situation, not in the cut situation, which we did. So now the point is at this particular point x, there are two forces which are continuously acting on. The first one is the force downward, which is VA minus W1, and the second one is the force upward, which is W2 minus VB. So now we can see from this diagram that at every point of the beam there are always two forces which are applied on, which is making every point in equilibrium, because as I said earlier, if the beam is in equilibrium, it has to be that every part or every point has to be in equilibrium. So in this particular case, this point is subjected to two forces which are, no doubt we can quite easily see that on the opposite direction. Now we can see if they are equal. Let's see, they has to be, first of all, to be in equilibrium. If they are equal, then this should be the equation. If I rearrange the terms, if I take this thing here and this thing here, this equation comes, which is the same as the equation which we have written there. So that means that these forces are also equal to make or maintain the equilibrium of the point. So this particular force which is applied on every point, that means the force which is applied radially, or I should say on the surface of the force, this particular force is known as shear force. In a simple language, we can say if the force with the abrasion, or I should say with the friction which is applied on, is a kind of shear force. Now we define the second term, bending moment. Now if we once again take this particular part also, now we are talking about this particular point. This distance is x. Let us assume that this distance is a. So now we want to know exactly what is the bending moment on this particular point. The formula of bending moment is that force into the perpendicular distance of the force from the point where we are actually taking the bending moment. So in this particular case, x is the point at where we want to take the bending moment, and a is the point, and this particular point, if we give it a name C and D, then at C point there is a force W1. Now we take the bending moment at this particular point x. We can quite easily see that VA is at a distance of x. There is a sign convention, but right now we are just analyzing this thing. If we conclude that the positive, or I should say, if it is giving a upward movement, then we call it as positive, and if the downward movement is there, then we call it as negative. Now VA is actually tending this beam to go upward. That means it is at this particular point, the direction of the moment will be like this for VA. In the same way, at this particular point, the direction of the moment which is created by W1 will be this. So that means that the moment by which is caused by VA will be taken as positive, and the moment caused by W1 will be called as negative. So what will be the bending moment at mx? It will be positive VA into x minus W1 into, if the distance will be considered this, that means x minus v. Now we talk about the second part. In this particular part, as we already know that W2 is greater than VB, that means the tendency of this beam caused by W2, or the direction of the moment caused by W2 on the point this x will be this, whereas the tendency due to VB will be this. That means that in this particular system, W2 will be considered as negative. So we can say minus W2, and if we assume that this distance is B, then the whole will be L. It will be L minus x. So minus W2 into L minus x minus B plus VB into L minus x. Now, there are two particular equations. This equation is also at point x and this equation is also at point x. But as I told you earlier, that if the beam is in equilibrium, then every point must be in equilibrium. So, once again we can say that. Now, before talking about this, we can say the resultant of this particular equation will be in this direction. That is, if I draw this point again, the point x, then the left part will give this type of bending moment, and the right part, this part, because W2 is greater than VB, that means the dominating factor will be W2, and it will try to create a moment which is opposite to the moment of the part left. That means at this particular point, both the bending moments will be equal. They has to be equal to maintain the equilibrium, but their direction has to be on the opposite side. So such type of moment is known as bending moment, or we define it as a bending moment. So the definition of bending moment can be that at any particular point, the moment which is created by any force is known as bending moment, and the formula is very simple. It is the force into perpendicular distance. Now, to understand these particular two things, that is shear force and bending moment, now we take an example, because the example will give us the right knowledge. If we take the same example, but this time with the values, the beam AB is having a length of say 5 meter. Say this particular force is 3 kilonewton and this particular force is 4 kilonewton. The distance from here is 1 meter, say 2 meter, then it has to be 2 meter. Now we have to analyze this particular beam. Now, as we were talking about shear force and bending moment, the point is that for any structure or analysis, any type of structure, we need shear force at every point, whereas in the same way we need bending moment at every point. To determine these two things, and it is difficult to locate the points because there can be n number of points in between the beam A and B. So we draw some diagrams which actually depict exactly the shear force and bending moment of the whole beam, which we know as shear force diagram and bending moment diagram, which we are going to draw for this particular beam. Now, first of all, we don't know the values of VA and VB. We know this particular equation from the equation of equilibrium, that is sigma V barabar 0, that VA plus VB will be this. So we can term it as equation number 1. Now the point is that we actually want to know what is the magnitude of VA and VB separately. For that we will use the which is the equation sigma m barabar 0. Sigma m barabar 0, as I already defined, that this particular equation means that every particular moment, every particular point, there is all the moment on the leftward sides are always equal to the moment of right side, but on the opposite direction. But if we are talking about the magnitude, that means at any point sigma m of left side must be equal to sigma m of right side. So we will use this particular formula to determine the magnitude of VA and VB. So if you talk about the point A, at point A, if you talk about the left portion of it, there is no force because there is no beam structure which is there, whereas in the right side the complete beam is situated, which is having a force VA 3 kilonewton, 4 kilonewton and VB. So if we take moments about A, what will happen, that at this particular point we need to determine all the moment caused by the components which are situated on the left side of A. In the same way, all the components which are situated at the right side of A. In the left side we don't have anything, so that means if there are no forces there, then this thing will be 0. But now in the right side we are having 4 forces, one VA himself, 3, 4 and VB. So we will start with first of all VA. For that there is a sign convention which is there. The sign convention says that at any section, if the bending moment is caused by the force on the upward side, either in the left side of the section or of the right side of the section, it is known as positive moment or sagging moment. In the same way, if the moment is caused at any section by the forces on the left side of the section or at the right side of the section, but if it is caused in such a manner, or I should say in the downward direction, then the condition says it is negative moment or hogging moment. So now, taking this sign convention, we will solve this, we will analyze this beam, or we will know the value of VA or VB. Now, what exactly will come here? There are 4 forces, VA, 3, 4 and VB. Now first of all we take VA. From this sign convention we can say that VA will be positive because it is causing the upward bending moment. Now what is the distance? Interestingly, VA is applied on A only. So that means the perpendicular distance or the distance from A to A is 0. Now this particular load, 3 kilonewton, it is causing a downward movement. That means this case is there. That means it is negative. Now, what exactly is the distance? The distance is 1 meter. So that means 3 into 1. Now, the second force, that is the force of 4 kilonewton, is also downward. That means once again this case will come and it will also have a minus sign. The distance will be, the distance of 4 kilonewton from the point A is 1 plus through 2, that means 3 meter. The last point is VB, the vertical reaction at point B. As it is giving a positive or upward portion, upward bending moment, that means this will be the case and the sign will come as positive. Now VB into the distance. The distance from the distance of VB from A is 5 meter. That means it will be 5. So now we need to solve this particular equation. Now we need to solve this particular equation. Quite easily we can solve it because there were 2 unknowns, but if we multiply anything from 0, anything with 0, it comes as 0. So that means 0, 0, minus 3, minus 12 and 5 times VB. If you solve this, it will come as 15 upon 5. That means, so it will be the reaction at B point. Now we need to know the reaction at A. We had equation 1. If we say, if we use this particular value with equation 1, the equation 1 was VA plus VB was equal to 7. It quite easily gives you the value of VA. That means 7 minus 3, 4 kilonewton. Naturally, it is also the upward direction. Now there is one more thing, which the doubt which comes in the mind of the student, that is it necessary to first of all take moment at this particular point? No, it is not necessary. We can solve this thing, or we can determine the value of VA is equal to 4 kilonewton and VB is equal to 3 kilonewton from the second approach also. In that particular approach, we could have taken bending moment at B also. How will we do that? I explain you. Now I am illustrating you that how this particular values of VA and VB also could have been taken from the point B also. Now we take bending moment at B. So it is quite clear that it is completely on the perception of the student or the will of the student to take the bending moment at A or B to determine the reaction. Let's see how we will do it. Taking the moment at B. Now all the forces on the left side of the B, whereas there is no force on the right side of B. That means sigma L sigma m of left hand portion will has to be equal to sigma m of right side portion. Right side, no force, so it is 0. Now we talk about the left side. In the left side we have 4 forces, VA, 3, 4 kilonewtons and VB. Now first of all we talk about VA. With our sign convention, as the force VA is on the upward side, so it will cause a positive bending moment. The distance of VA from B is 5 meter, we can quite easily see. So it will be VA into 5. Now 3 kilonewton is the downward side. So from our sign convention, the bending moment caused by 3 kilonewton at point B will be also on the negative side. So 3 into, now the distance which we can see is 3 kilonewton is situated at 2 plus 2, 4 meter away from B. So it means 3 into 4. The third one will be force 4 kilonewton. It is also on the downward side. So it will cause a negative bending moment, and the distance of it from B is 2 meter. That means like this. Now the last or fourth force is VB itself. VB is actually situated at B only. So it's quite obvious now that it will be multiplied by 0, and these 4 forces has to be equal to 0. Now if we will solve this particular equation, we can quite easily straightforward know what is VA. It is 12 plus 8, that means 20. So VA is 4 kilonewton, and from our equation VA plus VB is equal to 7 as the equation 1 which we gave, VB will be 3 kilonewton. So you can quite easily see that both the result are completely identicals. So that means that it is completely on the perception of the student to take this particular thing, the bending moment at point A or point B. He or she can take at any point. There is no problem in it. Now as we know the reaction components of VA and VB, now we will determine what are the shear forces at any points of the beam and the bending moments. Now first of all we will give the name on the points AC. So there are 3 portions in this beam, if we can see, portion AC, portion CD and portion DB. Now if we want to exactly analyze this particular beam with the point of view of shear force, then we have to take every portion separately, because otherwise there are n number of points. But the good thing is that we can see that the portion AC, all the points lying in the portion AC are having the same situation, that is at every point there is a left force which is VA, and in the right side there are 3 forces, 3 kilonewton, 4 kilonewton and VB. So first of all, for shear force diagram, we will take the portion AC. Now as I told you earlier that it is completely on the student that if we want to go from the left side to right side of the beam or right side to left side of the beam, because the analysis for both the cases will be completely identical, because the value of the point will be same for both of the cases. In a general way, generally we, for a simply supported beam, we go from left side to right side. Now we are having the first portion AC. In this particular portion, if we draw this particular portion, or if we draw this beam first and we cut a section in the portion AC, that is point X, then what will be it? If we draw it again in a separate way, then it will be the case we are having only one force in the left side of this particular section. Now what is the sign convention of shear force? The sign convention of shear force is something like this. That means it is bit different, or I should say a bit difficult from the convention which we were having in the bending moment, because in the bending moment the good thing was that at any section, either on the left side or the right side, if the moment is caused upward, then it is positive, and if the moment is caused downward, then it is negative, which is not the case in the shear force convention. In shear force convention, if the forces at any section, or if the forces which are subjected or any section, if they are on the right side and they are on the upward side, then they are positive, whereas if they are situated on the left side of the section, then and the downward forces situated there will be called as positive. In the same way, if any force which is downward but it is situated on the left side of the section, then it will be negative. In the same way, if any force which is situated on the right side of the section and is upward, then it is also negative. If we take this particular convention, then VA can be considered as positive because it is situated on the left side of the section, and in left side, upward are known as positive and downward forces are known as negative forces. So, the shear force Fx at point X will be, first of all, positive, and the value will be this VA. What is the value of VA? The value of VA is 4 kilonewton. So, Fx will be 4 kilonewton. Now, this particular equation, if we say it as equation 2, this particular equation is the equation for the shear force for the portion AC. So, that means what will be the range of this equation? This equation will range, if we say this particular section which we have taken is x meter from A, then the range of this particular thing will be 0 meter, that is at A, to x barabar 1 meter, that is at B, at C. So, this will be the values or limiting values of x is equal to 0 to x is equal to 1, which we have to apply on this equation. Interestingly, this equation is not having any x component. That means at x is equal to 0, it will be also plus 4, the first value, and at C, that is x is equal to 1 meter also, it will be plus 4. Quite simple. Now, if we talk about the portion CD. In the CD portion, if we take a section here, which is at y distance from A, then what will happen? If I draw this particular section alone, then it will be like this, a point Y. Now, at this particular section or this particular point Y, if we write Fx, then there are two components. First one is VA, which is positive from our sign convention. In the same way, the force 3 kilonewton from our sign convention is negative. That means plus VA minus 3. The value of VA is 4. That means 4 minus 3. That means 1. This equation is for the shear force of the portion CD. So, what will be the range of the value x? X is 1 meter at C, whereas x is 3 meter at D. So, now at x is equal to 1 meter, that is FC, it will be plus 1, whereas at x is equal to 3 meter, it will be FD, which is also plus 1. The reason because we don't have any x component in this particular equation. Now, there is a problem. The problem is that the equation 4 gives you FC is equal to plus 4 kilonewton, whereas equation 6 gives you FC is equal to plus 1 kilonewton. These two terms are same. So, now what the problem is, how it is possible that FC can have two values? Exactly. The issue is either it is wrong or there is something else which we are leaving. Obviously, it is not wrong. So, then what exactly the problem is? If we see this particular point very minutely, or if I draw this on some larger scale, this point C. Now, if we can see that if I talk about the point C, it is in portion AC also, and it is in the portion CD also. So then what is what we should do? The problem is, if we consider C in AC, then the value is plus 4, whereas if we consider C in CD, then the value is plus 1 kilonewton. So how will we differentiate the two values? The differentiation will be like this. The analysis is done like this, that as we are moving in this direction, if I talk about this particular point, that means the portion AC, then this AC portion is the portion C, or the point C which we have taken in AC is not exactly on the line of C, whereas we just assume this at something or little bit left of the C. That means you can say that this value x is equal to 1 meter is not x is equal to 1, whereas it is almost x is equal to 0.999 meter, something like this. That means that we are considering this particular point just left of the C point, because if we consider this point on the right side of C, then this equation which we wrote for the portion AC will be wrong. Why wrong? Because in this portion or this equation we have not considered the force 3 kilonewton, because it was not acting in this particular portion. If I see this particular diagram, whereas if I cross the point C, then obviously the 3 kilonewton load will come in the action. So to differentiate these two values, we are saying that this particular equation is not the equation of AC, whereas it is from A to just left of the C, whereas this particular equation which we have written is from the right side of C to the left of D. So what is the right way? The right way will be, we will write small l here and small r here. Now we can justify these values. That means at FC left, that means just left of the C, the shear force is plus 4, whereas when we cross C or we are onto C, the point, then the value is plus 1 kilonewton. So now we can quite easily say that even in point D also it will be a left and right. Now right now we are having just left. Now we will talk about the portion DB. Now in the portion DB we are having one more section. Let it be Z, distance Z from here. Now if we draw this particular section again, there are both forces which come into action, 3 kilonewton and 4 kilonewton, and this particular point is our Z. Now if we see this particular thing, now this particular section, then we can quite easily say that there are three forces which are acting on Z point in the left side, VA, 3 and 4. So if I talk about FZ, we can say this FY, now it is FZ. Now FZ, what is the value? Shear force VA is positive with this sign convention, 3 kilonewton is negative and 4 is also negative. That means VA minus 3 minus 4. Now what will the net value? The net value will be minus 3 kilonewton as VA is 4. So now this particular equation is the equation of shear force in between point D to B. Once again, interestingly, it is not containing any value of Z, which is the variable. That means that at Z is equal to, this is Y, we can say, this is also Y now. If we talk about Z, then Z here is 3 meter and here it is 5 meter. So Z is equal to 3 meter, then F, Z will give you FD, and we know it, and it will be right, then it is minus 3. In the same way, Z is equal to 5 will give you FB. There is no need on the corner points to write left or right, because at the point B there is no right. In the same way at point A there is no left. So FB will be 3. And interestingly, we can say that the value of 3 is the same which is the value of VB. So it is a kind of check in shear force diagrams or shear force diagram numericals that the last value, that is the shear force at B or the right corner side of the point, must be same as the reaction which we are having. but the exceptions are in the overhanging cases. Now we are having all the values. The values at FA is plus 4, FC left which is also plus 4, FC right which is plus 1, FD left which is plus 1, FD right is minus 3 and FB is minus 3. Now we are having all the values here. So we can quite easily draw shear force diagram. This is the original beam. The distance is 1 meter, 2 meter and 2 meter. If we draw like this, so that we can have the exact pattern of the values. Now we draw a horizontal line. This particular line is known as zero line, because at this particular line there is no shear force or zero line. Now we are having all the values, the value at A, C, D and B. First of all, we will point out the value at A. FA is plus 4. We can now FC left is also plus 4. FC right, that means the right side of C is plus 1. So we are still on C. Now FD left is pause. Now FC left was plus 4, FC right was 1. So now we can draw or stretch this line here. Now at D point, if we can see that FD left was plus 1, whereas FD right was minus 3. That means here it is. So now we can stretch this line like this. This value is 1 and this value is 3 and FB is also minus 3. So that means this. There is no need to write minus 3 here. The logic behind is that it is on the load side of the zero line. That means at this zero line, all the points which are on the upward side are positive, whereas all the points which are on the downward sides, which all are negative. That means this portion is positive and this is negative. We can give it some small lines. So this is known as the shear force diagram of this particular beam. Now what is the significance of shear force? Because the point is we must know all the significances whatever we are doing. Here the significance is that we are having a diagram which is giving us the complete values of all the points on the beam which are situated, the shear force of them. That means there. Now if we want to exactly know the shear force at any point x is equal to 4 meter from A, that means from A we need to know the shear force of a point which is situated 4 meter away from it. Let this point be E. So there is no need to calculate anything, because if we are having shear force diagram, then quite easily we can know this thing. We just give dotted line here. So this will be the value and the value is minus 3 kilonewtons. So one can easily say that the shear force at 3 is minus 3. Clear? Now the point is, we are talking about the second point, bending moment diagram. Now we are taking about the bending moment diagrams. The good thing is we have analyzed all three portions. So there is no need to once again go through all the portions again, or I should say, if I can just draw the small diagrams of it, it is also sufficient. If we talk about this, or if I draw the complete beam here, then now if you talk about the portion AC, as we said earlier, that in this AC portion, if we are having a section XX which is situated at x meter, Now we are talking about the bending moment at this particular point in the AC portion. Then what will be mx? As we can quite easily see earlier when we were analyzing this portion AC, that there is only one force in the left side of this particular section, and this particular force from our sign convention of bending moment, it is causing the upward bending moment. So it is VA, and the formula of bending moment is force into distance, and the distance is nothing but x meter. So now we can quite easily say that the equation which comes is 4 into x. Now first time we are having the x component here. Now the values or the limits of this particular equation is a to c, that means x is equal to 0 to x is equal to 1 meter. So at x is equal to 0, MA will be 0, and at C it will be 4 into 1, that means 4 kilonewton into meter. Now this particular value of MA is equal to 0 is already known to us, because when we were finding the reactions, we knew that we took bending moment at point A or point B, and we knew already that at point A or point B the bending moment will come as 0. Now we talk about the portion CD. In the CD portion, once again, if we are taking a section, let's see it is YY situated at Y distance, then what will happen, that at this particular point, if we are talking about the bending moment My, then at this particular portion in the left side there are two forces. First force is VA and the second one is 3. VA is causing positive bending moment and 3 is causing negative moment. VA is at Y distance from Y point, and important thing here is we need this distance, that is the distance of 3 kilonewton from Y, which is Y minus 1. It is Y minus 1 meter. If we put the value here, it is 4Y minus 3Y minus 1. Now there are two aspects. One can quite easily open these brackets and solve this particular equation initially, but my suggestion is not to do this, because the reason is there is no need of it. When we will put the values of y, then only anyhow we will solve this equation, and if we solve this equation here, then there will be some complication which can arise, which will not arise if we not solve this particular problem. So let's see, the range is 1 meter to, if you see the original beam, C point is at 1 meter from A, whereas D point is at 3 meter from point A. That means y is equal to 1 to y is equal to 3 meter. Now if we will put this thing, first y is equal to 1 will also give m at C, that is C. If I will put 1 here, it will be, this thing will be 0, and 4 into 1 once again, which is same as we got this thing. Because in the bending moment there cannot be anything left or right. Why? Because at any point C, the bending moment having the definition that force into the distance, and the point is any force in the world can cause no moment where it is applied, because the distance of that particular force from the point where it is applied is 0. So that means there will be always a check in bending moment values that m at C has to come as m at C. Yes, there is one exception, which is in the couple case. If there are couples which are applied on the beam, otherwise the bending moment at C in this particular equation must come the same as it is coming here. Now when we will put this particular value, that is 3 meter, then what will happen, 4 into 3 12 minus 3 into 2, that is 3 minus 1, it comes as plus 6 kilonewton into meter. Now we are coming to the last portion of dB. Now in this particular portion dB, what will be the equations? The equations will be, once again, let's having a section Z here, Z distance, that means mz will be, there are three forces on the left side of Z. One is VA, once again into Z, second one is 3. According to our sign convention, it is minus. The distance of 3 from Z is, this is Z, this is 1. So the distance is Z minus 1. The third one is 4, and quite easily we can see that this is completely Z. This is 1 plus 2, that is 3 meter. So the remaining distance is Z minus 3. No need to solve this thing. The only thing which we can do is by putting the value of VA, which is 4. So the equation is 4Z minus 3, Z minus 1 minus 4, Z minus 3. And the range, quite easily we can see from the original diagram, D point is at 3 meter from A, whereas B point is at 5 meter. That means the range are 3 meter and 5 meter. Let's see, from 3 meter we get MD. If we will put 3 here, this particular thing will come to 0, and this equation will be the same equation which we wrote here, and the values obviously will come as same. But one must check these values, because if there was a mistake here which he or she has done, then it can be repeated. So one should once again solve the problem, once again solve this equation, so that he can verify his or her answer. Now this is the check. We knew that MB is 0. It has to come 0. If it doesn't come 0, that means there is some mistake which we have already done. 5, that is 4 into 5, 20. 5 minus 1, 4, that means 12. And 5 minus 3, that means 8. Yes, it is coming 0. That means there is no mistake which we have done here. Now we will draw the bending moment diagram. Once again, for that, I will draw the original beam. The projections. Now the thing is, it is a tradition to draw both shear force diagram and bending moment diagram exactly under the beam, so that we can conclude from such diagram that what exactly we need to do. So let me first draw the shear force diagram which we drew earlier. The values were 3, 3, 1, 1, 4 and 4, and it was plus and minus. Now let me draw the bending moment diagram here. We have 4 values. MA is equal to 0, M at C is equal to plus 4 kN into meter, and M at D is plus 6 kN into meter, and M at B is once again 0. So first of all, MA is 0, then MB is plus 4, MC is plus 4, MD is plus 6, and once again 0. So if we draw, or if we will make a line which is meeting these points, we obviously know that it will not be a straight line with us, it will be inclined line. That also can be deducted from the equation which we had of the mx. At that particular portion it was 4x, and this equation is the equation of line which we know from the mathematics. Now the second one is this and this, and obviously all the values came as positive. So there is no portion of this bending moment diagram which is under the 0 line, and this will be plus. So and any particular point of this beam, if we want to know any value of shear force or bending moment at any point, quite easily we can produce the projection, and by this we can know this. So this is, students, the way how to draw a shear force diagram and bending moment diagram, and to use such diagrams to analyze the beam. Thank you.